Now we are talking about the multiplication of the operators. In general, the multiplication is non-commutative, right? So that's a very important property which is going to play a very crucial role in our discussion of uncertainty. That is, in general, except very special cases, the product in the xy order is not the same as the product in the yx order. However, it's associative, yet that is, and another important property is the Hermitian adjoint of a product. Well, obviously that requires a proof because it's a very crucial property. So it may be, we may wish to prove it. Okay. Let's try to demonstrate this last feature, which again will be very important in our further elaboration of quantum theory. Let's prove, or demonstration really. Let's not make a big deal out of it. Let's define y, let's pick an arbitrary state alpha. Define this as beta. Therefore, this is picked arbitrarily, because this the statements must be independent of the choice, really, arbitrary. So let's consider now x, y on alpha is, well, this is a bit redundant step, and we call this beta, so it is x beta. So what is the dual correspondent of this new state? Remember, we defined this as beta x dagger. That was the definition of the redundant state x. And what about the corresponding bra to this one? Dual correspondent to beta y dagger. Okay. Right? No. I'm sorry. Its dual is beta, which is alpha y dagger. Okay, that's the argument. So if I substitute this in here, I get alpha y dagger. Can you see it? That proves the theorem that the Hermitian conjugation of xy dagger is because normally we would have xy dagger in here, so xy dagger is the product of the y dagger, x dagger in the opposite direction. That's a very nice and quite straightforward demonstration, but very crucial one. It's going to play an important role eventually. Now comes the definition of another. We introduce another structure. Remember, we introduced an important structure before, the so-called inner product. Now we are introducing so-called outer product. Outer product of beta and alpha. Remember, inner product was alpha, inner. This is a reference to previous one. Inner product was alpha, beta. You get one bra from the bra space and one cat from the cat space and associate a complex number to it in this order. I already mentioned that the products, the orders of the products are very crucial. Now, this one is the first product is the cat one. The second element entering into the structure is the bra one. Claim. This is to be regarded as an operator. Well, we have to really demonstrate this. Let's put a question mark. Why, if it is so, why it is so? Why it is to be regarded as an operator? Well, before proceeding with the demonstration of this statement that this outer product produces an operator, not a number, as compared to the inner product, which was a number, we have to generalize this associativity of the multiplication of operators to a general multiplication procedure. This is, again, due to Mr. Dirac. He says associativity, let's introduce this before proving it. Associativity of multiplication in general. Which involving multiplication of cats, bras, operators. Remember, we have first noticed the associativity of the sum of the operators. Now really we are generalizing it, and Mr. Dirac calls it associative axiom of multiplication. Associative axiom of multiplication. You see, in a quick, careless reading, you may say, what's the difference? Well, there is a tremendous difference. Associativity of the product of operators or sum of the operators is something, and associativity of multiplications involving cats and bras and operators are another thing. So that's the reason why he changed the name and called it associative axiom of multiplication. And assume that it is valid for the multiplication procedure involving it. And in that sense, consider now, as an illustration, consider the following. Beta, alpha, acting on gamma. Both beta, alpha, and gamma are arbitrary vectors picked from the vector space in question. And I consider this the rather composite kind involved looking product. And use in here the associativity axiom of Mr. Drag, as x. And I can write it if, well, there is a, of course, you can think of it in a more involved sense, a product of that and that and that, and then put a larger bracket, everything in here. If I use the associativity of the axiom, associativity axiom applied to this complicated product, I can rewrite this as beta, alpha, and gamma. That is, take this product first and then bring it in. What is this? Well, this one is a number, right? Inner product of the alpha and gamma. And that is that's a ket. Then this, whatever this was, whatever this structure is, acting on a ket, gave you a ket times a number. Obviously, that's the property of an operator. So this must act like an operator. Well, I write it in short, operator, but a proper expression is can be or should be regarded as an operator. Okay, so it acts like an operator. So that demonstrates it. So what does it do? Notice the following. This operator is not just anything, right? Notice that there is the ket in here, beta, and it is written as the ket times the bra, but it is the ket. So this operator now rotates the gamma to the direction of beta. It projects the gamma to the direction of the beta, which appears in here, ket. Rotates the ket acted upon to the direction of beta. It's nice. So it has a very well-defined function and role, right? Whatever it acts upon, it projects that ket to that direction, appearing there. Okay, so let's demonstrate the Hermitian conjugate of this new operator now. So we have, let me define this, let's give it a name, x def. Beta, alpha, as a short, I define it as x. So I claim that the Hermitian adjoint of this is alpha, beta. Well, you may say it's trivial, not really a trivial thing, right? So how do we demonstrate that this is indeed the case? Well, the demonstration goes as follows. Let's pick demonstration. Let's consider an arbitrary gamma, and let's act on it by that x. What is the conjugate of this? Gamma x dagger. Okay, in principle, that is the conjugate of it. Well, let's write this. Left-hand side, what is this? This is beta, alpha, gamma. Now I can call this a complex number. It is, the meaning of it. So what is the dual, this is the dual correspondent. What is the dual correspondent of this rewritten version? It is beta C star, right? What is C star now? It is alpha gamma star, gamma alpha. alpha gamma, C star is gamma alpha. We use the property of the inner product. So let me use the associativity property again. What is it? It is gamma alpha beta. You write it as gamma alpha beta and compare with this. This must be the X dagger. Indeed, that's the demonstration. If X is defined as beta alpha, X dagger is alpha beta. Beautiful, really. It's a very simple and very powerful theorem, but it's going to play a crucial role. Now consider now as we are going to eventually move towards the matrix representations, as an illustration of it, as an illustration of the associative axiom's power. This was really used, this was demonstrated by using the associative axiom, really. A second illustration of the power of the associative axiom. So let me call it illustration 2 of associative axiom. Okay, so I'm not using this axiom in a very effective manner. For this, consider a quantity of this form. X is an operator, beta and alpha are bras and cats arbitrarily. Well, what's the meaning of the? We define a definition. Well, we can write, first of all, I can write this equivalently as follows. Right, if you want. These are two equivalent ways of writing it. Now, there's a common notation. Beta, X, and alpha. That's the notation. So you can, when you see an expression of this sort, you can either understand it that way or that way. Well, actually, it's a bit subtle. First of all, let's note the following. If I consider X and alpha thing, what is the dual correspondent of it? It is alpha X dagger, right? That's one observation. Well, let's call this, give this a name, gamma. So it's what we have done is dual correspondence of, this is just shorthand for X alpha. So what is then beta gamma beta gamma? This one can be written as beta gamma, the left-hand side, is gamma beta complex conjugate, right? That's the definition of the inner, one of the postulates of the inner product. And what is the right-hand side now, gamma beta? Gamma beta is the following. First of all, there is an overall complex conjugation. I put it outside. And let me fill in the inside. This is the gamma. Gamma is, the gamma bra is alpha X dagger and beta. Or alpha X dagger beta. And let's put the complex conjugation. But what was the left-hand side? Left-hand side was the definition of this, was beta X alpha. You see, this way, we have been able to prove this important theorem. Beta X alpha, we reverse the order, brings a complex conjugation, and the inside becomes X dagger. That is one of the very crucial theorems which will be of use when we are considering the Hermiticity property. Oh, by the way, if X is Hermitian, if X is Hermitian, of course, this becomes even simpler. Beta X alpha is alpha X beta complex conjugate when X dagger is simple. So for Hermitian operators, these matrix elements, when I move into the matrix element, is going to be rather important. Taking the, okay. Now, bases and matrix representation. Let's move into that subject because it will be really crucial without losing any time. But before moving into this matrix representation, I will matrix representation of operators. I will start with one of the fundamental theorems of the operator theory, an important theorem. It's really at the heart of quantum theory. That will show why we talk about observable, justifies why we take the Hermitian operators to represent the observables. Okay, for a Hermitian operator, A, well, it is the book's notation. X's are general operators, A's are for Hermitian operator for a class, smaller class. For a Hermitian operator A, the eigenvalues are real. That's the first part of the theorem. Second part, the eigenvectors corresponding to different eigenvalues are orthogonal. You'll see it, particularly when we take up the uncertainty problem, how crucial a role this general theorem will play. It is really almost a trivial theorem, although so powerful that proof is so simple, makes it really very important. Now consider the eigenproof. Consider the eigenvalue problem. As customary, we use the small letters to denote the eigenvectors and eigenvalues, and we label them by the discrete index AI, although generalization to continuous spectra is trivial. So that's the eigenvalue problem. So what do we do is, first of all, we multiply this from left by AJ, AI, AJ, AI. So we have passed from the original equation to this equation. Next, we take the dual correspondent of this original eigenvalue equation, write it in the following fashion. I'll go to the left. There's not much room in there left. Okay, so what is the dual correspondent of the equation? AJ star AJ. When you go to the dual of the left-hand side, it's Hermitian, therefore I don't need a dagger being Hermitian, otherwise normally going to the bra space, I replace the bra and the operator with a dagger. It's Hermitian, no dagger. Numbers to pick up a complex. And instead of I use J. It is a generic label, regardless. I'm free to use any index I like. And now I multiply this from right by AI. What do I get? I get the AJ, AI, AJ star AJ AI. So that's the other equation, new equation. So we have this equation as compared to this equation and use the fact here. Let me write it. It's such an important statement that hermiticity, A dagger A, is used in going to the dual. Otherwise, I would have had A dagger in here, which I use the fact that it is A dagger is equal to A. Now you have these two encircled blue equations. Subtract these two equations side by side. Subtract side by side. The left-hand sides are the same, right? The A sandwich between AJ and AI. So left-hand side is 0, right-hand side is AJ minus AJ star AJ AI. Okay, so that's the equation which I need to solve. I can solve it in two shots. First, I take I is equal to J. If I take I equals J, AJ minus AJ I AI is equal to 0. For any null arbitrary eigenvector, well, of course, it's trivial 0 if A is null, but that doesn't mean anything. We have to take non-null. So this is, according to one of the axioms, that's non-zero and positive for non-null. Positivity is not important. Non-vanishing, being non-vanishing is important. Therefore, if it is non-vanishing, the only thing that this equation makes sense is that this should be 0. AI is equal to AI complex conjugate. Okay. That is, AI is equal to AI complex conjugate. That's the first part of the theorem. Eigenvalues are real, demonstrated. Second part, we have to show that eigenvectors corresponding to different eigenvalues are orthogonal. So let me go back to this equation for the part 2. Feed this in. That conjugation is fed in. Now take AI, I different than J. If I is different than J, then the left vector is non-zero. The only way then is AJ, AI is equal to 0. So that's the only option left. Therefore, that's the second half of the theorem. When I is different than J, then these vectors are orthogonal. Inner product being 0 is the general definition of orthogonality in this Hilbert space. We expect we are moving in that direction eventually that eigenvalues of observables be real. Obviously, if it is observables are the operators corresponding to quantities like position, momentum, energy, whatever. And in order to establish contact with the physical reality, we have to think of something, and eigenvalues are the first things which come to our mind. They are the things probably which are measured at the laboratory corresponding to the physical reality. If so, then we expect to have entities, operators with real eigenvalues. And Hermitian operators happen to be those entities with real eigenvalues. That's why we say we have to deal with the Hermitian operators. Okay. So if we normalize these eigenvectors, well, we can put a twiddle on top, but you say after the normalization still retain the same notation, then I can write this result of this theorem, the second part of the theorem, saying that AI on AJ is delta IJ. Indeed, when I is equal to J, it's 1, corresponding to the normalization. When I is different than J, it's 0, corresponding to the second half of the theorem, that different eigenvalues, eigenvectors corresponding to different eigenvalues are orthogonal. Question, as we are moving towards really a quantum mechanical, a physical interpretation of this mathematical structure of Hilbert space containing complex vectors and Hermitian operators with real eigenvalues and orthonormal eigenvectors. And we have to make physical sense out of this. And how are we going to do that? For this, we have to question the completeness of these eigenvectors. Remember, at some point we said an arbitrary state vector, a vector in this state space, can be expanded in terms of a given complete basis. The completeness was sort of an ad hoc assumption there. And it, as I said, it's the Copenhagen interpretation. It's the basic axiom of quantum theory that a state can be expanded, and the expansion will contain all the information which is supposed to be contained in this arbitrary state. You see, it really boils down to this simple expansion postulate. And in that sense, we need the completeness. We say here that in the, if I rewrite it, this expansion postulate, I have written it in the following fashion. And I runs from 1 to capital N. N is the dimensionality of the space, and dimensionality is dictated by the physics. In the Stenger-Lach case, if there are 2 possible outcomes in an experiment, it is 2-dimensional. If it is 3 possible outcomes, and is in the spin 1 case, it is 3-dimensional, etc. So the number of linearly independent vectors should be 2 or 3, depending on that number. That's the expansion postulate. We say that this is the basis of the space, usually orthonormal, and should be complete by construction. Question, what if that particular basis, which we haven't really identified with anything there, we said let it be a complete orthonormal basis. Now, can we take it to be the eigenvectors of a Hermitian operator. If so, if it is eigenvectors of a Hermitian operator, orthonormality is by default. Therefore, let me determine the coefficients using that orthonormality property. Suppose this is the eigenvectors of a Hermitian operator. How do I determine the coefficients and to attribute a physical meaning to those expansion coefficients? I can do it in the following manner. Let me project this along an arbitrary member of the basis set. Let's call it AJ. Some I, Ci, AJ, AI. I'm just using orthonormality, that is being normalized and orthogonality together. Orthonormality, delta ij, carry out the I summation, this becomes Cj. Whatever appears in here is appearing in here. So this C coefficients are nothing but the projections, really, because that's the inner product of it, alpha along the AJ direction. Let me substitute back into that expression. I AJ alpha A, sorry, now I'm using J in here, but I in there, so it is AI. I use the Mr. Dirac's associative axiom involving vectors, bras, and cats and operators. Let me move this to here using associative axiom. AI alpha. It's really nice, isn't it, that way? If you look at the left-hand side and right-hand side, then you see the following in here. You can establish the analogy of this with the ordinary vector. For instance, you can write analogy. V is the three-dimensional vector. Here are the basis vectors, the sum 1 to 3 in the three-dimensional space. Coordinates, how do you find the coordinates? This is the projection of this along the EI. You see how, particularly this one, both of them analogous, but this one is really exactly analogous to this one, right? This way of writing. But what follows from here is another property of these orthonormal eigenvectors of the Hermitian operator that we have considered. It is this sum, which is running over all space, is an identity operator. It involves what it involves. It involves A1, A1, A2, A2, all the way to AN, AN, which is the identity operator. And then that raises the question, what is the physical meaning of any one of these terms entering into this sum? What is the meaning of this, for instance? There is no sum in here. Notice that when there is no sum, we have to indicate. Given I is either 1, 2, 3, 27, whatever. What is the meaning of it? The meaning of it is rather trivial. It projects, when it acts, this is an operator, obviously, because the sum of its identity, each individual of them is an operator, as we have seen before. They act like operators. It projects any arbitrary vector when this acts along there. If I define this as lambda I, if I act by the lambda I on an arbitrary vector, then what do I have? AI alpha, Ci. So indeed, it projected this along that particular vector. It's a projector. So it involves the projectors associated with any ket, eigenket. The sum of all these projectors add up to 1. And that is the so-called completeness relation. So when we are considering eigenvectors of Hermitian operators, we have to remember that they are orthonormal by default, being eigenvector of a Hermitian operator by default orthonormal, and they are also complete vis-a-vis, thanks to the basic expansion postulate of the quantum theory, which is at the heart of the Copenhagen interpretation. Together with that, it proves that it's complete. Orthonormal and complete. This is an ideal property you expect from a basis. In order a set of vectors to be used as a basis for the space in question, they have to satisfy these properties. They have to be orthonormal and complete. Then any arbitrary vector can be expanded in terms of them, and any information which we expect to be contained in that state vector will be contained in the expansion terms altogether. And that will lead us to the measurement process. I think that's a good point to stop. And next week we are going to go on from this point. We are going to proceed further from here. Okay.